I'm guessing you started getting lost approximately when he started doing cistrons.
Yeah, that's it.
So, why did you get lost? What's the usual excuse I give you?
Assumption? No.
Hmm.
Yeah.
No, it's always the same assumption. Usually, it's going to be the same thing only. What
Yeah.
assumption here? Which one am I going to ask you to question?
That cis will be always less stable, maybe.
No. That is not the assumption even.
Because of
Going too deep into the assumption here. I want you to question cistrons. How do you define cistrons? That is the question, right? At the
Yeah.
core, something
Yes.
to do about cistrons is funny. That's why you got
Yeah.
confused. Fair enough.
Yes.
Is that a better way of putting it now?
Yeah. That's it.
So, effectively, something about cistrons is funny. So, let's go to cistrons. Define them, please. Let's go into the definition of cistrons. How do we define cistrons?
Cis, it's when two same atoms or same groups are attached to the same side of double bond. Same side of a bond, pretty much.
Okay.
Not necessarily double bond.
Okay. Now let's start questioning the hidden assumptions here. Your definition is not wrong. You were careful enough to be as detailed as you could be in your definition here. So I can't fault you with that also now. So now let's examine what you said a little bit closely. You said across a double bond are basically be a bit more inclusive.
Any bond. Oh,
Any bond there is an extra statement which you have to give.
any bond which has different
When I said
atoms.
inclusive, what did I mean really? You know about cistrons in two cases already properly, right? You've done ring, you have done this.
Huh.
Double bond.
Yes.
Be
Oh,
inclusive.
ring also. Yeah, ring too.
Be inclusive.
Oh, in restricted
Sorry?
rotation.
Hmm?
Restricted rotation
That
atom.
is going to be conditioned for cistrons.
Oh.
I'm not looking at conditionality. I want you to
Mhm.
define the condition. What is it? The statement in a way in which it includes both. So, what was interesting in the double bonded case? See, right now, what is the complexity which has been added in? Your definition was correct,
Hmm.
right?
Yeah.
But now, in this case, an extra complexity has been added into the game, correct?
Yes.
What is the complexity which has been added in?
Confirmation. Like it can.
That's it. That's stop. You got the correct word there. Conformers.
Okay.
Correct.
Yeah.
Now you need to start seeing in your definition of cistrons with respect to the double bond and the ring there, what were the conformers you had assumed them to be? Because you defined it in that case according to that situation, correct? At
Yeah.
that time, conformers you didn't know about. But does that mean conformers did not apply there? Or was it just that it was hidden?
Hidden.
So apply. Let's try it.
Okay.
Now, calm down a little bit and start questioning your assumption a bit more carefully. Double bond, it is a little bit more tricky, right? Why is it tricky in the double bond? Because they look the same,
Yeah.
right? They look the same. But if I want to see conformers more carefully, where can I see it more carefully? In the ring.
Yeah.
Correct. So let's draw a simple ring case. A simple ring case is this. And if I'm going to be having, say, hydrogen towards methyl away. And if I'm going to be having hydrogen towards methyl away, this is something which can be called as a cis. Is it applicable or not applicable?
It is, yeah, cis trans applicable, but yes, it's cis.
Yes, applicable so
Yes.
far.
Yeah.
Okay, all right. So this is going to be something which will be the cis conformation here, right? Trans will
Yeah.
be the methyl will be on opposite directions, right?
H will be replaced with CH. Yeah.
Okay, all right. So this is going to be having some hidden assumptions here, which are going to be hidden from which point of view?
Trigon.
Conformer point of view.
Oh,
Correct?
yeah.
What are they? If I want to put conformers for C1 and C4 and C3, what will they be? What will the conformers be?
Different
What structure
structure.
is this?
Hmm.
What structure is this? The
What structure?
cyclobutane.
Cyclobutane, yeah.
Cyclobutane, what type of a fellow is that?
Planar.
So if it's planar, what should it look like?
Oh, yeah.
Right?
Yeah.
So now, what is this then? This has to be something like this. Correct? That means these two guys are what really? What is the hidden assumption here inside the definition?
Same side of the bond. Oh, same conform. Yeah.
Correct? Huh?
Yes, sir. Yeah.
That is a hidden assumption.
Yeah.
When you are having definition of cis trans, how do you define cis and trans then? Define it more carefully now. When you are going to be having two carbons which are having inhibited rotation attached by a bond. And in this system where there are two carbons which are having inhibited rotation attached by a bond, you are going to be having both of them in the same conformation. And now, if the common groups are on the same spatial side, we call them cis. And now, if the common groups are on opposite spatial sides, we'll call them trans.
Spatial sides, okay.
You understand the way to project the definition now clearly?
Yes, sir. Yeah.
By adding conformer into the bit now. Are you clear with what I'm trying to explain here?
Yes, sir. Yeah.
So till now, what did you have? You had definition of cis trans in your brain properly.
Yeah.
Your confusion started when conformer was added into that definition without explaining to you how to add it. Correct?
Yes, sir. Yeah.
So you need to clarify how to add this extra variable to a function which you already understand. That is a mathematical function. Cis trans isomerism is a mathematical functionality which you have learned. To that mathematical functionality, an extra variable called conformer was added. You did not treat it like that. You saw this as the same cis trans in different case. Wrong. It is cis trans, but with an extra variable added in now. You have to start seeing what is the effect of that extra variable on the cis trans definition. On that black box as a function. Then you can now apply that logic now. So let's start. Let's say I'm going to be looking at cyclohexane now. So if I'm considering cyclohexane, when I'm defining cis trans, I am defining in planar. I am not defining in some random structure which is non-planar. I am defining in the planar. So cis-trans is something which is defined from a planar perspective, where all the fellows are in the same conformation. That part is clear so far, yes?
Yes. Yes.
So now, before we go there, cyclohexane, when you discuss the other structures, the standard structures, and the basic ring flipping, I'm assuming till the ring flipping you understood.
Ring flipping.
Discussed how the ring converts from chair 1 to chair 2.
Yeah, it goes up like this. Yeah.
And you discussed the energy profile diagram for that.
Yes. Yes.
So I'm assuming you have done that twine,
Yeah.
thing.
Yes. Yeah.
And if you have discussed those, you would have discussed what is going to be equatorial, what is going to be axial.
Yeah. That's why I was kind of confused.
No. Let's not jump there. You would have discussed that. Okay. Let's talk about cyclohexane bonds now. If I'm having the cyclohexane in a, what to say, planar form here, right? So I will have one bond coming towards in each of these carbons. Correct?
Yeah.
And simultaneously, I will also be having one bond going away.
Yeah.
I'm simply going to call the fellows that are coming towards me as axial, other fellows as equatorial. I don't give a shit what they are. They're just names. One is one, the other is the other. I don't care what they are called. Sincerely. It doesn't make a difference. Let's not dwell on stupid names first.
Okay. Yeah.
They are terms. We'll get to why they are the way they are when we need to get to them. So for now, basically, one is towards, one is away.
Yeah.
Right? I'm just going to call the towards as axial and away as equatorial. Blindly, I'm going to name it. You know that axial and equatorial are opposite fellows.
Yeah.
That much is fair.
Yes.
Then my naming currently is perfectly acceptable. All
Yes.
axials, all equatorials. Towards, away. Now, let's start trying to see things a little bit more clearly. In this current configuration here, we are having carbon, 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 carbon here. 1, 2, 3, 4, 5, and 6. So all 6 carbons here are in the same configuration. So Y, 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 or inverted, 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 inverted. Correct? That's what planar means.
Yeah.
So let's start with the cis. If I talk, say, cis 1,2 dimethyl,
Exactly.
what should that mean?
There are two
It should mean
methyls. Yeah.
I'm going to be having
Both at axial or both at equatorial.
Or I should have it as equatorial as methyls.
Yeah.
Correct?
Sir, but then it's half chain, no?
Cis. No. Stop.
Oh.
Stop. There is no half chair shit right now. What is this? What are we looking at?
Just cis. Planar.
We are looking at planar.
Yeah.
All right. Because I know how to define cis and trans only for planar. Right? That's what my original definition of cis and trans was applicable for, correct?
Yes, sir.
Yes or no? Because ultimately, you have to start thinking what you define cis and trans for. Do not misunderstand that when you're connecting the pieces. We have cis trans as a function which has been defined properly mathematically. The problem came when we added conformer into the mix. Correct? So now we need to add the conformer in a very, 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 very controlled manner so that we can observe exactly what is happening. Do you understand what I'm trying to do over here?
Yes, sir.
That's why I tried explaining that to you mathematically at that point. We are having a black box called cis-trans, which has a certain set of functionalities, a certain set of rules. I have another black box called conformations. Originally, I had learned what this mathematical function called cis-trans does under a certain set of circumstances.
Yeah.
I do not know how that applies in a different scenario. I want to understand that. Right? That's what we are trying to do here. But to understand that, I need to make sure I'm going back to the original definition with which I had defined it.
Yeah.
I will not taint that randomly without understanding the connection there. So I'm going to do it in a proper planar form. This is the planar one. All are in the same configuration. So if I have cis 1,2 dimethyl in this, all right, what is going to be happening is in the cis 1,2 dimethyl, my C1 and C2, if they are in the same YY conformation, then in that YY conformation, I can say this is going to be axial or equatorial. Because they have to be on the same goddamn side. Correct?
Yeah.
This is cis. Now, let me try to see what is going to be happening from a staggered projection if I have something like that. And try to observe what that means truly. So, this is basically YY conformation, correct? So, I have hydrogen here, hydrogen here, hydrogen here, hydrogen here. Let's say methyl here and methyl here. This is basically what's happening.
Yeah.
Right? Yep. This is not hydrogen here exactly. This is going to be connection to ring. So, let me rub this guy off. So, this is not a hydrogen here. This is not a hydrogen here. This is a ring connection. Correct? I can imagine.
So we can draw this structure for any two carbons, adjacent carbons, right?
We are not going to be looking for everything here. We are looking at one space. One place where we are looking. Stop thinking about the connections there.
Okay.
Zone in and try to see what's happening at this level here. Zoom in here. So there's some ring connection. I don't care what this is. This doesn't matter to me. Skip that shit. Okay. So these are in same conformation. This is going to be cis as of now. Correct?
Yeah.
Now, this is in the planar where they are both in YY. But in reality, your more stable structures are almost always going to be staggered.
Yes.
So you need to know what happens if I convert this Y to an inverted Y. Right? So originally, I basically had, this is what I'm basically putting the axial here actually. Correct?
Yeah.
Because I took equatorial as away and I took axial as towards. That's the definition I took, na?
Yeah.
Right. So equatorial was supposed to be going away. Axial, I took it as towards me. So now let's flip this now. I'm going to take this as carbon 1. I'm going to take this guy as carbon 2. But if I convert this from a Y to an inverted Y for carbon 2, how will this be changing? I'll have hydrogen still here. I'll have methyl here on the axial. Correct?
Yeah.
This is ring nonsense. I don't care where this goes. This will become ring because this is going to be going inverting like this.
Yeah.
Okay. What will be happening to the other fellows there?
They will go down.
They'll basically invert completely.
Yeah.
So effectively, what's going to be happening is something like this. So I originally ended up having a group in this place like this, which is originally exactly in this fashion like this. So now I'm going to be rotating it and making it like this. So what was originally coming towards will now be inverted completely, correct?
Yeah.
You got that or not? I mean,
yes, sir. Yeah, understood.
Cool. So let me get out of this thing here. So when you're drawing it here like this, now this will be a CH3 and this will be a hydrogen. Meaning now in this carbon here, this is going to look like equatorial. This will look like axial. So what is the scenario here? This is still going to be C1, C2, correct? So if I want to talk about cis 1, 2 dimethyl in a planar form, it is going to be equatorial, or
Or axial.
axial. But if I change this guy from a planar to chair form, chair form is proper staggered, correct?
Yes, sir.
What should it become? It will become equatorial axial or
Or axial equatorial.
axial equatorial.
So when you change it to chair, they just swap.
Yeah. No,
Okay.
don't randomly swap though. No and swap. Because the game will
Why?
change in every stage.
Well, then
Let's
here it doesn't
show
matter
you
whether
here.
you put
Calm down, calm
axial
down.
and
You're starting to understand, but you're starting to basically randomly connect shit right now. Wait. Stop doing your random connections. First, come back to what are the various conformations. So if I'm looking at planar can be written C1, C2, C3, C4, C5, C6. Can be written as Y, 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 Y. If I take chair is going to be Y inverted, Y inverted, Y inverted. Right?
yes.
So now, if it is C1, C2, your definition is for planar. System's definition is perfectly the way you imagine it is for planar. Correct?
Yeah. Yes.
Same side is going to be the way it is going to be cis, opposite, not trans. Correct?
Yes.
But chair 1, 2, there is a difference. Where else do you see a difference? If I take C1, C4 combo, in planar it is YY. In here it is Y inverted Y. Correct?
Yeah.
So if I'm looking at cis 1,4 dimethyl, then for the planar, I would have had it as axial or equatorial. Correct? Now, if I flip this for chair, this is still remaining YY, but this Y is now becoming inverted Y.
Yes.
So what will happen here? It will be axial equatorial and equatorial axial. Correct?
Yes.
But now try for 1, 3. If I have cis 1, 3 dimethyl, what is going to be the case? In the planar, it is going to be equatorial or axial.
Yes.
Correct?
In chair also it will be same.
What should it be?
Equatorial.
Why?
Because it's already, they're always going to be the same.
Both are in the same conformation already.
Yes. Yeah.
You understand the rules to be followed here properly now and how to adjust them?
Yes.
So I'm guessing now your cis trans for the shit will basically start playing into clarity.
Yes, sir. Yeah. Makes sense.
Now, the next will be basically how to bring in both.
Yeah.
Same principle applies everywhere. Basically, the principle, if it is core correct, things will stitch nicely.
Okay. Yeah.
So in the board there, what's going to be happening? What is the conformer for the conformation for the board there?
Both it will be Y inverted Y.
Did I give it last time or not?
I don't think you did.
I would have. Yeah, I did. Boat I normally give. This is boat.
Yeah, that's right. Yeah, Y, that's what I was saying. Yeah. Or reverse. Yeah.
Yes, it is not perfectly staggered, it's partially staggered.
Yeah. Yes.
That's the idea there. So for the board there, you have to be slightly more careful. C1 and C4 will be in same configuration. C2, C3, C4, C5, C6 will be in same configuration.
Okay. Yeah.
So this is basically the game behind this. Next, I'm guessing you still have a few issues with respect to this, which are going to be on the lines of why in some cases some groups are going to be present in some places more stably. Is that thing, have they asked questions on those lines already?
Yes. Yeah. Repulsions as well. Yeah.
Okay, all right. So effectively tertiary butyl crap or 1,4 hydroxy, that kind of crap has started.
Yeah. Somewhat. Yeah. Those stuff. Yes.
Okay, all right. Which ones we have as doubts? Because the fact is this, you're never going to be able to clarify all of them. Why? Because each of these individually is a special case.
Hmm. Sir, I
So,
mean, though.
yes, tell me.
Sir, so always the bulkier groups should be away from each other when no other stuff are at play,
See,
like
there is
charge.
no, see, how do you react? Do you always react the same way if the same stimulus is given to you?
No.
No. Then why the hell do you expect molecules to? You're a collection of them, dude. You're not going to be, means they are not going to be.
Hmm.
So never make hard and fast rules to follow in chemistry. You do that, you're basically fucking yourself.
Hmm.
Unnecessary. You're adding unnecessary bullshit assumptions.
Yes, sir. Yeah.
I started realizing by now that assumptions are the key game to really understand shit beyond a point.
Yeah.
Right? So if you really want to enjoy chemistry, you have to start questioning your assumptions. In physics, also,
Hmm.
there are a lot of assumptions. It's just that in physics, they are a lot more hidden.
Yeah.
And they know how to hide it very beautifully.
Yeah.
So, you have to start realizing what you want. And
Yeah.
for someone as intellectual as you cannot stand without understanding. It is not going to feel correct.
Yeah.
So, so let's throw that aside. Let's start accepting that understanding is what you want. And each case is going to be unique in its own way. There will be something
Hmm.
or the other unique. There are going to be some commonalities, but don't make the generalization the one which you have to remember.
Okay.
Remember that this guy is unique. Remember, everything else similar to that guy is going to be similar. I won't care about it, but this guy is unique. So
Okay.
let me explain what I'm trying to say here. Do not make a generalization with respect to bulky group. Avoid making a generalization like that. Make a more specific generalization for alkyl groups if they are present. Don't call them bulky. If there are specifically fatso-alkyl groups, MS Chauhan mein this exception is seen in 3 questions, which means my teacher has given me this exception in class. That is how the game works. So you are going to be having a bunch of exceptions which are going to be given to you one after the other in class. The way I'm sensing it, your teacher is very good at collecting these exceptions because he has been systematic about learning his subject over the years. He has not yet connected all the pieces perfectly, but your teacher has been very systematic about collecting these exceptions nicely.
The Gauss effect ones.
Yes, yes.
Yeah. Those.
Practically
Yeah.
almost all of these. I can sense the kind of things which he has probably given you. I'm
Yeah.
guessing
FF
he's given you
CL
tertiary
CL.
methyl exceptions. He's given you dimethyls. He's probably given you 1,4 dihydroxy, 1,4 fluorohydroxy,
Huh.
1,2 dimethyl, 1,3 dimethyl. He would have given you. He would have
Yes.
given
Yes.
you
Yes.
1,4 tertiary butyl also probably.
One
All standard
tertiary
things.
butyl.
Anyway, so
Yeah.
point here is those are all like standard basic exceptions. If you have connected all of them together, then you don't need to give them individually. Things will, the connection is basically how to visualize cis and trans, how to connect
Hmm.
the cis and trans into conformer there. Because
Okay.
now you can see how they are supposed to be connected. Once you can see how they are supposed to be connected, then you can play the game. You don't need me to sit and hold your hand at every stage of the game now.
Hmm.
Now you know what is the way to flip, what is the way to get it done. Do
Yeah.
it. Figure
Okay,
it out.
sir. Yeah.
Now I will give you this. The way to connect the pieces is when you're having a bulky group, like say tertiary butyl. It is basically something where there is going to be multiple connections drawn and multiple bonds. When I say bonds, multiple electron pairs which are specifically located in specific regions in space because they are bonded. Bonds are chains. All right. So you're going to be having multiple pairs of electrons forcibly located in specific regions of space. That is what a bulky group is going to be. So one bulky group and another bulky group obviously will want to be as fucking far away as possible. Necessarily. Only under one condition will they be interested in coming closer. When I say bulky, it applies to lone pairs also. Only under one condition will they be interested in coming closer, which will be if they can do intramolecular hydrogen bonding.
Yes. Yeah. F and O. Yeah.
Now, to understand the intramolecular hydrogen bonding, you need to unfortunately see the structure of cyclohexane a little bit more closely. That unfortunately means I'll have to sit and make that structure now. Give me a couple of minutes.
Yeah.
Not a couple of minutes really. Another minute or so. So effectively I have like 3 carbons done here. I'll add 3 more. So I'm just going to connect 6 carbons bluntly, and you will be able to see what's happening there straight away. Basically, currently your visualization of chair form is not perfect. So this is the actual chair form. You see it?
Yes, sir.
Now I will show you how to position it. Watch how it is. A stupid split. That thing is crap. Okay. Watch what's happening. Watch how it is positioned. Can you see there are 3 bonds on which it is sitting on the thing?
Yeah. Axial bond.
Exactly. And there are 3 bonds up here. So the axial idea here is these are the guys which are on the vertical axis.
Okay.
All right. Equator is going to be on the horizontal axis.
Everything other than those, pretty much.
Correct. So these guys are all going to be on the equatorial here. They're all going to be on this plane. Horizontal plane slightly up and down.
Yeah. Yes.
One pointing up, one pointing down. One pointing up, one pointing down. One pointing up, one pointing down. So that they have enough space away from themselves. And there are 3 fellows on top and 3 fellows in the bottom. So these 3 are in the same spatial region, roughly.
Yeah.
So if I have a fat group here, here, and here, they are problems.
Okay.
What are these locations? This is carbon 1 na. This is 2. This is 3. This is 4. This is 5. That means carbon 1, 3, and 5. This guy was 1. This guy is 3. This guy is 5.
Yeah.
So carbons 1, 3, and 5 are the ones which are actually going to be in the same planar region if they are axials. Have a look again.
Okay.
Don't try to visualize too much. Our brains are not that capable of doing it. Someone as intellectual as you is not going to be that sharp at visualizing. I'm guessing your Rubik's Cube solving nonsense, you would have started solving better once you learned the solution.
Yeah.
And you would not have figured out the Rubik's Cube by yourself.
No. Yeah.
So, yeah. So, you are not a visual fellow. You are an intellectual. So, let's not go into that part there. So, here, you're going to be having, this is one fellow here. These 3 are the ones which are going to be on this plane here, the axial fellows.
Yes.
Correct? The ones which I'm going to be pointing out with my hand here.
Yes.
Right? These 3 are going to be alternating carbons. This is carbon 1 na. This is carbon number 3. and this guy is carbon number 5.
Hmm.
And their axials are the ones which are going to be in the same plane,
Yes.
the plane of this stage. That means their axials are the ones which are going to be having maximum repulsions.
Hmm.
So if I have fatso groups on any of these 3 axials,
Yeah.
that's bad. They will have repulsions. How will they fix the repulsions? They will switch them into equatorial. Basically, let me put the groups and show you. That will be easiest actually. Let me put the groups there and you'll understand that more clearly.
Hmm.
Up is easier. I'll put it on up. Putting it up is easier. Basically, the same thing now.
Yes, sir.
In up, you can see more clearly also.
Yeah.
So as you can see here, you're having 3 blues on top here, correct?
Hmm.
Now, the point here is this. The blue is not one fellow there. The blue can be imagined like this.
Okay. Yeah.
Each of these is a fatso like this.
Hmm.
What happens then? If this fatso is having more fellows connected,
Yeah.
it becomes very fat.
Yes.
So if each of them is going to be, let me add one more fellow also onto this. If there are 2 groups attached like this,
Yeah.
on this one fellow here, and if there's going to be one more like this over here, each of these blue, what to say, circles, which you see is like this big fellow here. What will happen then? This guy also wants space. This
Yes.
fellow also wants space. This fellow also wants space.
Yeah.
There is not that much space available, literally.
Yeah.
So when you're not having enough space available, you will literally have crowding happening there. So this and this are now getting crowded by this fellow here.
Yeah.
And that is basically what is going to be a big problem when you are going to be having fat groups present in axial locations which are alternating. So these are alternating carbons, as you can see, right? So this is carbon 1 now. This will be carbon 2, carbon 3, carbon 4 here, carbon 5 is this guy now. So the ones which are having groups are 1, 3, and 5. Now, if these are in axials like this, they can change. How? They just flip. Now, I didn't do anything. I just flipped it around.
Yeah.
Just flipped things around a little bit around. Now look
Yes.
at where they are. Now this is going in one direction, that is going in one direction, that is going in one direction. And
Yeah.
yeah. And as you can see, they are all now in equatorial.
Hmm.
They are in equatorial, they are all in some direction. So if I put one fat group here, let me show you by putting the fat fellow here. If I replace this with this guy, as you can see, it doesn't matter. It's going in one direction. This will go in one direction. This will go in one direction. So I can happily put fat groups now.
Yes.
You're understanding the idea here? So when
Yes,
there
sir.
are fat groups present in alternating locations, what's the key learning from that? Never put fat groups in alternating positions
Axial.
on axials. Why? Because if you put them on axials, you're basically putting them in the same,
Increasing the repulsions.
which means you're purposely increasing crowding. So when you can have a hydrogen bond possible in that case,
Then you can put.
then you put them.
Hmm.
So if I have, say, cis 1,3 dihydroxy, write it down. Cis 1,3 dihydroxy system. What do I want? It's a dihydroxy, correct?
Yes, hydrogen bond is possible.
Exactly. That means I want the two OH groups as close as possible.
So best to put them
So,
in axial position.
exactly.
Hmm. So, but then if you put them in, okay.
You want them as close as possible.
Would any other repulsions be greater than,
Think,
like
think,
you?
think, think, think. Don't ask me the question. You think. I didn't give you anything else over here. Right? I just bluntly said cis 1,2 dihydroxy, 1,3 dihydroxy.
Hmm.
This is the best one. So axial would be better because I can have intramolecular hydrogen bonding being a possibility here. Now, if I had, say, 1,2 dihydroxy or 1,4 dihydroxy, what would I prefer in that case?
Then you would want to
If it
want
is
to be
cis,
the
if it is cis, what would I prefer?
cis. Okay,
Hmm.
1 second. Uh,
Let's go with 1,2 first. 1,4 is a little bit more complicated. 1,2 first.
hmm.
1,2, they are never
One,
going to be having intramolecular in this case,
correct.
right? So I don't need to give a
Different
shit.
planes. Yeah.
Hmm. So I'll go with, it doesn't matter.
Axial equatorial or equatorial axial.
Both are same. It doesn't make a
Hmm.
difference. It will depend
Hmm.
on the other groups which are present, how the others are going to be modeling themselves around this. Same way, if I'm going to be having 1,4
One
also, it's
four.
going to be similar, excepting with one issue there. In the boat conformation in 1,4,
Oh, then you can put axial there.
not just axial, you will have the fellows that are axial being pointed like this. The other fellows will be going like that. Axial fellows are pointed like this now, you can have
Oh,
hydrogen bonding.
correct. Okay. So then what decides whether it's boat, half boat, or like, sorry, half shell?
Stability, not
Okay,
for
so
individual pieces, but for the overall thing.
okay, but then
Overall,
so,
overall, total stability.
oh, okay. So suppose 1,4 dimethyl would have different structure than 1,4 dihydroxy.
Obviously,
Okay, yeah.
because the 1,4 dihydroxy has a possibility of hydrogen bonding. The
Okay.
1,4 dimethyl has no chance of that. So 1,4 dimethyl will obviously prefer chat.
Yes, sir. Yeah.
And it will try to be in opposite angles completely, opposite directions completely.
Hmm. Yeah.
Whereas the 1,4 dihydroxy will prefer the boat. Under the case where it can have hydrogen bonding. If it cannot have hydrogen bonding, what will it prefer? Chair as well.
Hmm.